40. Predict the valence electron molecular orbital configurations for the following and state whether they would be stable or unstable ions. Okay, so we have our molecule here. We have Na2+. Now, in this case, we have to determine what the valence electron molecular orbital configuration would be. And in order to do this, first things first is we just have to find out how many valence electrons are we working with here. So I know that I'm dealing with sodium, right? Because Na is sodium, and they're telling us that we have 2 sodiums. So if I take my sodium and I have 2 of them, each sodium, right? If we look on the periodic table, sodium is in group 1, right? So that's pretty important here. And if you're in group 1, you have 1 valence electron. I'll just say val electron. So 2 times 1 is a total of 2 valence electrons. Now, in this case, right, remember, sodium is in group 1, period 3. So it's got 2 valence electrons in period 3, right? Think of your 3s orbital, right? It's got basically 2 electrons in the s's. But now, unfortunately, we have to remove 2 electrons. That's what the plus sign means, right? You lose 2 electrons. So, from the 2 valence that I had, I have to subtract 2. And now I'm down to 0 valence electrons. But unfortunately, the math does not understand chemistry, right? Math is just math. Math is just calculations. But what does 0 valence electrons really mean? Well, this just means that you'll have 0 valence electrons in your n equals 3, right? The biggest energy level outside of the nucleus. So we're talking about your 3s and like your 3p, your n equals 3. So where would be the valence electrons then, right? Well, if we banged out all of the valence electrons in the 3rd ring, and if we just put this into perspective, let's just say that this was sodium, and it has n equals 1, it's got n equals 2, and it's got n equals 3. On n equals 3, there's no more valence electrons. So the valence electrons are not in the 3rd ring anymore. Bye-bye. And now they're just down to n equals 2. And you got a full set there, right? Because in order to go from n equals 2 to n equals 3, you got to have a whole set. And a whole set for n equals 2 is 8 electrons. 2, 4, this is 6, 8. So instead of saying 0 valence electrons in the 3s, 3p, n equals 3, you really have 8 valence electrons in your 2s and 2p because you got a full set. But remember, we're talking about 2 sodiums. Each sodium would have 8 valence electrons. So if you have 2 of them, you got to do 2 times 8. So 2 times 8 vals. We're now looking at the max amount of 16 valence electrons. And then we're going to take it from there. So this was all that math to figure out how many valence electrons are we working with for the 2 sodiums. Now I have to write my electron molecular orbital configuration. And it's a mess. But there's 2 different types depending on where is your element located. We got groups 1, 2, 3a. This is supposed to be 4a, not 45. I don't know why I put a 45. I guess because I knew 5 was coming up. So 5a, and then we have group 6a, 7a, and 8a. Now we just said before that sodium is in group 1. So we're over here. And because sodium is in group 1, we will be using this molecular orbital configuration. So I'm going to take that out of here. And if you want, we could, get rid of this because we don't need this anymore, right? We're not dealing with group 6a, 7a, or 8a, but just know that if the element was in those groups, you would use the other one. Now, the reason between these two is because of sp orbital mixing. this type of concept is not for a Gen Chem, course. So it's best to just memorize that there are 2 of them. So this is the one that we're going to use. Now, I left markers for what S's and what P's we're using. And since we already stated that we're in 2S, 2P world, we're just going to fill that in. So this would be your sigma bond for your 2S. Anytime that you see a star, that means antibonding. So for ever bonding, you got an antibonding counterpart. You got 2PYs, 2PZs, 2PXs, and then you got all the antibonding equivalents. Now, we just have to throw in how many total valence electrons. And in this case, we got 16. So those valence electrons go in the upper corner of each parenthesis. Kind of just like in a regular valence electron. And remember, if you're only stating 1, you only have a max of 2. So I have to go from left to right until I get 16. So 2 electrons will be in the first 2s sigma bond. Then 2 electrons would be in my antibonding. Now for this one, I have 2 different orbitals. So 2 for this one and 2 for this one. That's a total of 4. I keep going. This one, I need 2, right? And now I have 2 orbitals grouped together. So this is 4. And then my final antibonding orbital has 2. And let's see, do we have a max of 16? Well, 2 plus 4 plus 2, 4 plus 2 plus 4, that's 10, 12, 14, 16. Aha! So this would be the valence electron molecular orbital configuration for Na2, 2+. So that's the first answer. Now we just have to figure out, well, will this be stable or unstable ion? Is this a stable or an unstable ion? When they're asking you whether it's a stable or an unstable ion, they're secretly asking you for the bond order. Because the bond order is going to tell you what type of bond is going to be made between those 2 sodiums. And the formula for the bond order is this. And maybe I'll just make this a little bit lower. And maybe what I'll do is I'll just bring all this a little bit up. We'll box this off just to say, hey, we found the first answer. Oh boy, what happened there? Is it going to do it again? I hope not. Okay, there we go. And now, for the bond order, we just have to find out the total number of bonding electrons and the total number of antibonding. Now keep in mind that those antibonding ones are the ones in the stars. So, let's see here. How many bonding electrons and how many antibonding? Well, for bonding, it's all the ones that you do not see a star in the upper right-hand corner. So for bonding here, let's see, I have 2. This is antibonding, so that's not going to count. These are bonding, because I don't see a star, so 4. This one's bonding, because there's no star, that's 2. And all of these are starred, so that's antibonding. So 2 plus 4 is 6, plus 2 is 8. So I have 8 for my bonding. How many for my antibonding? 2, because there's a star. I'm scanning. I got star, star. That's a total of 4. And then I got another star. That's a total of 2. So 2, 4, that's 6, 7, 8. So I got an 8 in here. So my bond order would be 8 minus 8 divided by 2. And 8 minus 8 we know is 0, right? And anything, 0 divided by anything, is going to be 0. But what does this actually mean? Well, if you have a bond order that's equal to 0, that means that literally there is no bond that is going to be formed here because it is not stable. So if you have a bond order of 0, no bond. No bond, no girl. Does anybody know where that's from? Well, not the no bond part, but what was it? I think it was no trip around the world, no girl. I've actually seen that speech in person, I think 4 times. One of the highlights of my life. Let me know in the comments if you know what I mean. John Oliver did a quick little video on it. But let me know in the comments if you know what I'm talking about. Anyway, so no bond, which means that it's unstable. This is an unstable ion, and it will not occur in real life. Wonderful. And those are your 2 answers. So let's just box this off. Beautiful. And call it a video. All right. I hope this helped you out. Let me know in the comments. Subscribe to the channel. Thank you for viewing the video, and I hope you're having a great day out there. Keep studying hard, and I'll talk to you in later lessons. Bye-bye.